Okay, everyone. So let's begin our final session. This session, Joonsuk Jung from Yonsei University QIYA will be presenting about decoding across LDPC codes. So let's invite our speaker.
Okay, good evening, everyone. I'm Joonsuk of Yonsei University, and I'm going to talk about how to decode across LDPC codes. This presentation is advised by Professor Jae Park of Yonsei University. Uh, I'll be talking about how to perform quantum error correction and how quantum error correction codes has gone so far. Let's start with classical error correction. A basic example of classical error correction is the repetition code. Our classical binary data may have bit flip errors where 1 goes 0 and 0 goes to 1. To prevent this, we repeat the 1s and 0s to make it fault tolerant. Here, you can see that our code words gets noise and decoded by the majority vote. Detection of the errors is done by the parity check matrix. The parity check matrix is a matrix that gives a 0 when we product the code words like this. This means that all the code words in its null space. When the parity check matrix is multiplied to some noisy codes, it gives a syndrome like 1 or 0, 1. The tenor graph on the right gives visualization of how it's done. The squares are the checks of, which are the rows of the purchase matrix, and circles are the bits of the purchase matrix. So the error correction code gets robustness that increases as the size of the code increase, where you can see in the left. But if the physical error rate is very high, the error correction code, error correction system fails. The example on the bottom is the logical error rate plot of a classical repetition code, where you can see the threshold is about 50%, which is quite reasonable because it is 1 and 0, and the decode is majority vote. So that was the classical error correction, but things get a little bit complicated when it goes to quantum. Because our qubit has two types of errors, bit flip errors and phase flip errors, the error correction code must be able to detect both errors simultaneously. We need measurements that doesn't change the observable, which we call the stabilizers. The stabilizers gives parity checks, which are called syndromes, where you can see here, the stabilizer is projected on the states, and we get the state is preserved, and we get a syndrome, which is plus or minus. The overall process of the error corrections looks something like this. We get an error, and we measure them with X and Z stabilizers. And from the measurement, we get syndromes X and Z, which we decode with decoders and make it error correct. Lastly, we do error correction. This example here is the process of minimum weight perfect matching decoder on a toric code. The toric code, this is the toric code's tenor graph, which you can see as it has a plane of qubits and X and Z measurements. And the minimum weight perfect matching decoder gives a threshold about 10.3%. I'm not going to talk about the details right now. So that was the quantum error correction. Okay, we'll go to the how to decode QLDPC codes. Before moving on to QLDPC codes, we give a formal definition of the error correcting codes. All the classical codes are binary linear codes, which are defined right here. The dimensions of the classical code is given against the rank of the parity check matrix, which means if we have a low rank or low density parity check matrix, we have more dimension, which means a logical qubit can present lots of states. Okay, and the distance is defined as the minimum distance of the code words. And in the quantum code, we have, you can see it right here, the HX, which parity check matrix X and parity check matrix Z is orthogonal. And the other parameters are defined as follows. So we have the definition, but how do we construct a quantum code? The construction is done by hypergraph product. The hypergraph product looks like something like this. We get two classical codes and we get a product and we get a quantum code. The quantum service code is made of two repetition code and quantum toric code is made of two ring codes, which is classical. The details are like this. I'm not going to see about the details. This brief explanation. We product the rows of the classical code and the columns of the classical code to make it orthogonal to each other, X and Z. So our main topic, quantum low density parity codes. The low density is, as I said, the low density parity check codes. QLDPC codes is where each qubit is connected to a bounded number of qubits. The toric and surface codes are the QLDPC codes with qubit degree of 4. The qubit degree means that each qubit had 4 stabilizers connected to each other. For a long time, toric code and surface code was close to the state of the art, which was the overhead about 1,000 qubits. That was the main problem of the toric and surface code. But recent development in hardware made it possible to have long-range connectivity to make QLDPC codes with much less overhead possible. And the recent research had the overhead about 50 qubits. Also, the strength of the QLDPC codes is that it has lots of platforms supportable for the QLDPC codes, like neutral atoms, ion traps, photonics, and superconducting qubits, which are the main platforms. So we have the family of QLDPC codes where you can see right here the Kitaev toric and hypergraph product and others that I really don't know. As you can see, the dimension and the distance order comes together, which means linear overhead for the size of the code. So we have a great QLDPC codes, but how to decode them? That is the BPOSD decoder gives the general solution to this problem. First, the BP belief propagation is a general decoding algorithm for classical LDPC codes, which can be applied to any tenor graph like this. The strength of BP is that it is extremely fast, which runs in linear time. I'll show briefly how it's done. First, we set the belief for each bits according to the prior knowledge that we have about the error rates. Second, we perform a propagation via the code of tenor-graph. The propagation is referred as messages. This is the implementation of a message passing algorithm and product sum variant. We propagate the messages according to these rules. As you can see, we set the beliefs and propagate the messages, and finally get the output. This works quite well for linear LDPC codes. But if we do it on the toric code, the results look something like this, where you can see that the distance increase as the distance increase, the logical error rate increase, which is not a working decoder from our previous insights. The problem is the trapping sets. The trapping set is usually occur in all various QIDBC codes because of the cycles that fails to convert to a solution. As you see in the animation, we set the beliefs and propagate it, but that doesn't converge to a solution. So for QIDBC codes, we need a post-processing method called order statistics decoding, OSD in short. So the OSD is a post-processing routine that always returns a solution. This is the overall process. We input the syndrome and we have a BP output. If the BP output is true, we just use it. But if not, we use OSD to get a right solution. The point in using OSD as a post-processing method is that BP gets quite a good solution, where you can see that where we have seen that BP gets a quite good solution. So we use OSD. How do we use OSD? We use BP output as a light decision, which means the BP gives probability that it gives a good solution. And we discard the low probability qubits and get a full rank sum matrix. The full rank sum matrix always has an inversion, so we can get a direct solution for the problem. So the BP applying to the toric code, we can get a working decoder right here, where you can see the distance increase as the distance increase, the logical error rate decreases, and we get a threshold of about 9.4%. The detailed parameters are like this, and this is in the Python package called LDPC, so you can see through. So that was a BPOSD. I'd like to point out some discussions where first, what are the bottlenecks of the BPOSD? The BPOSD's bottleneck is the processing time of OSD, which takes cubic time according to the block length. Hopefully, BPOSD gives since BPOSD gives a general solution, hopefully we can find a much faster local solution for other problems. And the second question is that can quantum error correction code be done by can be the solution for FTQC? But this is not quite true, because according to the theorem below, we know that implanting universal gate set is challenging in general. So we need other methods like magic state distillation and T-gate sorts and sorts. So that was my presentation, and for this vacation, I'll be reviewing the things that Google has presented recently. So anyone interested, this is my LinkedIn, so contact me. Thank you.
Okay, so if you have any questions, please feel free to ask.
The error mitigation is about the hardware, I think. It gives, I don't remember all the details, but it is not not the core of the quantum error correction. The quantum error correction code is the core of the error correction. The mitigation is subroutines, I think. But doing error mitigation is quite good because where you can see that we have a threshold. The threshold is the point where our quantum error correction system fails. So we have lower physical error, then we only have to use little bit of qubits to make a logical qubit. So yes. Any questions? Yes. Kind of logify something for the beta algorithm converges the BP well converges in a linear quantum circuit, so that is not the case for the quantum, because if we have a linear code, then the density will be quite high, saying that the connectivity will be 1 or 2. Yes, but I believe there is loops, then there's no guarantee that BP will converge. Yes. Those quantum circuits does that. Yes, so we yes, that I think there will be some other local solutions for using the BP, I think, but I don't remember. So thanks. Yes, I think it's quite good because of the speed, but yes. But also there are both BP LSDs and BP. Yes, I don't remember. Sorry. No more questions, then I'll stop right here.
Okay, let's thank the speaker again.